Hello everyone, I'm Changhan Shin. In this semester, I'm going to teach some details on solid-state physics and its applications for electronic devices, including p-n junction diode and Schottky diode or metal semiconductor diode. So let's take a look at the syllabus first. Herein, uh, there we go. So in March, I'm going to tell you some course introduction first and general material properties, followed by crystalline structures, including face-centered structure, simple cubic structure, and diamond structure for silicon. And then we're going to study how the carriers charge the particles within a crystalline material is moving. So to understand or to describe how the carriers are moving within a crystalline material, we need a tool. So that is named as energy band diagram. So we'll understand it. Afterwards, we're gonna have some physical concept of charge, effective mass, and the number of carriers in intrinsic materials. So you may have a chance to imagine how many free electrons are available in silicon material. Whenever you are making a DRAM NAND flash memory, how many free electrons are available intrinsically? So we will learn, uh, have a chance how many free electrons are available. And then to better and to better express how the free electrons are moving around, roaming around within a crystalline material, we have some, not, we need another concept that is density of states or DOS. And to describe the energy that a certain electron has, we need another metric that is a Fermi function. Afterwards, by combining density of state with a Fermi function and probability of finding out electrons in a silicon material, we can build up the equilibrium distribution of carriers. Okay? So most of these contents will be taught in March. Afterwards, we will focus on how the electrons are and holes are moving around in a silicon material. In other words, we need to figure out the carrier actions. So in summary, we can simply say DDR to describe how electrons and holes are moving in a silicon material. The first D in DDR is indicates drift. Drift means a charged particle such as electron and holes are moving around under the electric field. Okay, so to better describe how electrons and holes are moving, we need a few more concepts. That is one of which is mobility. So how mobile a electron is. Okay, so mobility, the concept of mobility is closely associated with the effective mass and average scattering time. Average scattering time means uh, how long uh, a certain electron needs to be scattered with another electron in a silicon material. Okay. Afterwards, we're gonna build up some concept of resistivity, and then we can estimate quantitatively the resistance value in the unit of ohm. Okay, in linear circuit class, you may have many chance how to estimate the total equivalent resistance in a series connected resistive network or parallelly connected resistive network or circuit. Okay, so we will see some fundamentals. Where does the concept of resistance comes from? Okay, then the second D in DDR to describe the carrier action in silicon material, the diffusion will be understood. So the very first to describe how much electrons and holes are diffused out in a silicon material, we need to build up an equation describe diffusion current. Okay. Oh, definitely we will learn the drift current as well in part of drift. Then by summing up drift current with the diffusion current, we can understand and describe the total current in silicon material. Okay. So many so many basic concepts associated with the solid state physics will be studied, definitely including recombination generation and others, diffusion length, quasi-Fermi levels, and others. Okay, then we're gonna take a midterm exam, maybe end of April or 7th or 8th week. Then in May, since we have learned some very fundamental parts of solid state physics, and this course is offered for the graduate students in Department of Electrical and Computer Engineering. So I'd like to put some more focus on uh, PN junction diode as well as metal semiconductor Schottky diode. So some fundamental solid state physics knowledge can be used to describe how the PN junction diode is working, how the MS Schottky diode is working. So in May, we're gonna induce and derive some all the detailed steps to get to have ideal diode equation under DC bias. And afterwards, in June, I guess we will understand some uh, alternating current AC characteristic of PN junction diode. So small signal admittance followed by transient response as well. So maybe storage delay time. This metric is widely used to evaluate how the PN junction diode turns on and off. Okay. Afterwards, I guess we'll study MS junction first to better uh, have all of you follow up some details of PN junction diode. Anyhow, MS context, Schottky diodes will be taught, and some practical consideration in understanding MS junction diode will also be taught. Then we're gonna take a final exam at in the last week, okay, maybe mid June. Okay, all right. So that's all about the syllabus and some detailed content that we are going to study this semester. Okay, all right. And I have checked the calendar, and we have a one holiday on yes May 5th. Okay, Children's Day, Korea. So we're gonna have some makeup class in on May 6th, I guess, at 6 p.m. to 9 p.m., I guess. So we will see that. But at this moment, let's set up this time, May 6th, okay, Wednesday night. Right. And now I hope everybody can see my PPT slide. Um, so let's take a look. There we go. So in the very first slide, I'm going to tell you some general material properties, which is corresponding to the chapter 1.1. Ah, I forgot to introduce the textbook. Textbook is Semiconductor Device Fundamentals, written by Robert F. Pierre. So that book is available in on-campus bookstore. Otherwise, you can purchase it through Amazon.com or other online shopping mall. Okay, so in chapter 1.1, we will go over some general material properties. For example, what is the semiconductor and how to understand the resistivity, conductivity stuff. Afterwards, we're gonna see some atomic structure for crystal material. First is polycrystalline, and amorphous material, which is kind of non-crystalline material. Afterwards, we're gonna study some notation, how to describe a certain direction and plane in a crystalline material. Okay, so let's do that from now on. So here we have a very simple question. What is a semiconductor? So when you are high school student, you may answer for this question, well, semiconductor is kind of half of it is conductor and half of it is insulator. Well, in some sense, that answer is quite reasonable. So let's take a look at some details in this slide. So here, conductor. So conductor means it has a humongous number of ton and tons of electrons. So those electrons can easily flow the current. Well, herein, let me ask one more question. What is a current? Well, current, the concept of current is quite simple. First, we need a charged particles. Maybe in crystalline material, or more specifically in silicon crystalline material, what is a charged particle? Well, definitely, it is a free electrons. So free electron is charged particles. Well, in more detail, it is negatively charged particle. So once those free electrons are moving around in a material, we can simply say that it is now flowing current. What, what about the playground for those free electrons? If those free electron is moving in a simple at a simple manner or easily, we can say that the resistance toward those free electrons is very low. Okay, resistance is very low. In other words, the conductance, inverse concept of resistance, is very high if the free electrons in conducting material cannot be faced with any energy barrier height, any energy barrier, whenever those free electrons are moving around in a conducting material. So in that sense, you may capture or you may intuitively understand the conducting material or conductor can have very low resistivity. So many physicists that has done many experiments and they found that the resistivity, right down here, resistivity in the unit of ohm times centimeter, okay, resistivity denoted as a rho, symbol low in the unit of ohm times centimeter conductor. The range of resistance for conducting material is 10 to the minus, let me double check the number just in case, uh, minus 5 to 10 to the minus 6 ohm times centimeter. Then what about another material which is standing right on the opposite side of conducting material? That is an insulator. So insulator, basically it doesn't have too much free electrons and other charged particles. Because of that, insulating material or insulator cannot easily flow the current. So intuitively, you may say like that. Or insulating material has huge barrier for free electrons to move around. On top of that, the insulating material doesn't have too much free electrons, so that we can conclude that insulating material has high resistance or high resistivity in the unit of ohm times centimeter. Okay, so many physicists has done experiment And it turned out that the resistivity of insulating material is in the range of 10 to the 14 to 10 to the plus 18 ohm times centimeter. So please compare the resistivity value for conductor against resistivity value for insulator. I guess a more than billion times difference. All right, then, well, this course is definitely to focus on some physics in semiconductor material. So now is a good time to understand what the semiconductor is. Since we have learned the conductor and insulator, right? So you can intuitively answer that while semiconductor has intermediate resistivity compared against conductor and insulator. Well, that makes sense, and that's really reasonable answer. So as described herein, the conductivity of semiconductor lies between the conductivity of conductors and insulators. So many physicists has done some experimental work, and it turned out that resistivity of semiconductor is in the range of 10 to the minus 3 to 10 to the plus 3 ohm times. Here, one quick note is that in the device community, in the field of electronic device, uh, all the unit for length, area, and volume is based on centimeter. Whenever you are describing how long a certain site length is, please use centimeter instead of nanometer, micrometer, and others. Well, definitely when you have a chance to design a integrated circuit chip, all the unit for describing the length and area is based on micrometers. Okay, but in news article you may have more chance to see the nanometers. Okay, anyhow, in this lecture, centimeter based length, area, volume will be used. Okay, all right. Okay, so that at this point, so please remember the answer for the question, what is a semiconductor? In terms of resistivity, which has the unit of ohm times centimeter, the semiconductor has intermediate resistivity or intermediate conductivity compared against resistivity or conductivity of conductor and insulator. Okay? Maybe in midterm exam, if I'm asking this kind of question, in terms of resistivity, please describe the semiconductor. Then you may answer for this question. Okay? All right. So let's move on to the next one. On the bottom side of this slide, you can see that the general crystal, some top view or animation, how the atoms are placed in each material. So here in polycrystalline, in the middle amorphous, which is kind of a non-crystalline material. Okay, and on the right hand side you can see the crystalline material. So can you guess any difference in between them? You can simply answer like that. Well, definitely this black color dot indicates a single atom. Okay, so this single atom or single dot are placed very regularly. Okay, under a certain rule, the silicon atoms are placed in a material. However, in case of amorphous material, think about how the black dots are placed. No rules, right? There is no governing rule for those black dots are placed in a material. In this case, we can say that this material is classified as amorphous material. What about the left side one, polycrystalline? I would say here, locally, all the silicon materials are regularly placed. And take a look at this specific area. So all the silicon atoms are placed along a certain direction. But compare the direction in this area and that area. Can you see that the difference in directions? Right. So locally, silicon atoms are placed regularly. However, globally, I saying again, globally, take a look at the holistic view of this material. Then the silicon atoms are not following a single rule. Therefore, locally crystalline, but globally non-crystalline. Then how to describe this material? So people has come up with a new name, polycrystalline. Okay? So poly means many, right? So many crystalline material has built up a material, right? So material-wise, uh, in terms of the rules for atoms to be placed in a material, we can classify the material into three different one. One of which is crystalline, the other of which is polycrystalline and amorphous. Okay, so remember how the main difference between crystalline, amorphous, polycrystalline. So again, always think about the silicon atoms are placed following a certain rule or not. Then you can simply classify the material into three different ones: crystalline, amorphous, polycrystalline. Okay, so that's all for the very first lecture note. The very first lecture slide in the first lecture note. So let me give you some break time, and I guess I have some time to upload this movie clip in a uh, iCampus. If I'm recording like a 75 minutes long movie clip, then I'm going to maybe fail to successfully upload huge, big chunk of movie clip file into the cloud. So let me stop here and see you in the next movie clip. Okay.